Hello sir, this is Umaeshwer. I'm from group 7 and I worked on this presentation with Sudarshan, and our topic is called photo tourism. So this paper was our primary reference material, and the authors propose a novel end-to-end solution to virtually transport people to historical sites or monuments. Let's see what this paper is about. So there are three main objectives: organizing photo collections from aggregator websites, 3D reconstruction of a site using images from multiple angles, and rendering the 3D model and coming up with a simple UI to navigate through the images. So let's see each of these in detail in a few minutes, but before that we'll have a look at the image dataset. On an aggregator site like Google Images or Flickr, you can find thousands of images of a particular monument, let's say the Taj Mahal. So they are taken from different angles and cameras and are unordered. And there is also very limited information available about these images, and that too it is there only for a few images. How do we make sense of this data set for our problem? So here is where computer vision comes to the rescue. So we use a technique called 3D scene reconstruction that makes a rough 3D model of the monument using the provided images. There are 4 steps to this: key point detection and description, key point matching, structure from motion, and georegistration. First up, we'll see finding and matching key points. So key points are detected and described in each image using the SIFT algorithm. And SIFT is preferred because it is invariant to transformations. Once the key points are detected, we can match the key points in different images using RANSAC. So this creates a so-called set of tracks which are matching key points across multiple images. Now we'll have a look at something called structure from motion, which is the most important part of this scene reconstruction technique. It gives a sparse model of the site while also estimating the relative position and orientation of the cameras. It's an elaborate method, so we'll see it again step by step. Okay, so first we select a single pair of images among the dataset which have the maximum number of matches. So these two images shouldn't be identical if a single homography transform is applied to either of them. So we then introduce a new image which has the largest number of tracks with this pair. So the new image is suitably morphed using a discrete linear transform, which is a method to compute the homography matrix. So we repeat the previous 2 steps for the remaining images in the dataset and join them using 3D line segments. On projecting the key points from this image database, you can find the sparse 3D model of the site. Now, doing this procedure for thousands of images is bound to be expensive, and here are some hacks to solve that. First of all, why should we add just one image after every iteration? We can add more also. Simple thing. And sometimes the tracks, some tracks might not be having the same weights as others. So we can remove these outliers after every iteration. So this was the SFM algorithm. We'll now see how to optimize this algorithm. Have a look at this example. So we are trying to reconstruct a model of a cube using 3 cameras, which is camera 1, 2, and 3. So take a particular point on this cube, let's say the corner point P1. So on projecting P1 to the surface of the cameras, we will get 3 projection points. Now here is one important thing to understand. So the calculated projection point on the cameras and the observed projection points need not be the same. So our algorithm has to reduce the distance between these points so that they are almost identical. So the sum of these distances is called reprojection error, and that is what we are going to minimize in this algorithm. And naturally, the best method to do this is least squares because it deals with distances. Also, least squares is computationally not so expensive, so it is fine if we go ahead with it. So the last step of scene reconstruction, which is called georegistration, is not as complicated as it sounds. We take a top view of the 3D model and superimpose it over an overhead map. So as you can see in the image on the right. So we manually move the model around to best fit the map. In case we know the location of some camera points accurately, we can add a term to the objective function during SFM optimization. So that's it from my side. Now I'll hand over to Sudarshan to explain about rendering and navigation.
Hello sir, this is Sudarshan and I will be taking over the rest of the presentation. Let's begin first by examining the UI of this application. As you can see in the image shown, there is an overhead map on top right, image thumbnails at bottom, navigation buttons at left, and the main scenery in the foreground. So for the basic rendering of the foreground, we use ransack to fit the plane onto certain key points. A few parameters are adjusted and surrounding images are rendered with some translucency and blurring parameters which are like tweaked based on the images. So now let's move on to the next section. The key part of rendering is to give viewers a sense of smooth transition. Now there are two main ways to realize the transitions. The first method is through camera motions. We have a source and final destination image. We match the points of the two images and give a direct transition, somewhat similar to the diagram shown here. Say instead we want to transition but also keep an object in focus. In this case, we orient the camera to the mean of the selected points before the transition. So the second method is something called as view interpolation. This is a more intricate technique and also has two subtypes. The first subtype is called as triangular morph. We basically render a mesh and blend the two images in proportion, creating a sense of continuity. This is not an accurate method though because it's prone to distortions. In comes the second subtype, planar morphs. This is the one used by the authors in the paper, and this involves projecting the two images to a common plane, then cross-fading between the projected images. This is efficient and also more practical. So after the rendering, let's move on to the navigation part. The free flight navigation is one of the features that enables the user to experience a standard 3D game type navigation using the navigation buttons. The next feature that we have to talk about is the object-based browsing. So here we see how similar two images are to zoom in or zoom out. So let's take, for example, the statue on the right. If it's to be seen, then we can expect all the key points of that statue to be present in the left image as well. This intuition is mathematically expressed in terms of ratios to figure out relations between these two images. The next feature is relation-based browsing. This is the answer to all questions like, show me what's to the left or right of this photo, or let me take a step back and view the scenery, and so on. The last feature, navigation feature, is called overhead maps, and this gives an accurate sense of location to the user on ground level. So with this, let's move on to the other additional features that are present. So let's say we want to add a new image to this 3D model to better help the reconstruction. So we have to follow the following steps. For example, drop an image into the approximate location where the image was taken. Then run the SFM, structure for motion pipeline, iteratively till all the parameters for the new camera are optimized. So this is how we can enhance certain scenes. So the next thing is annotating objects. So now we have to use CV based techniques to annotate different images across the database. Also, we like to determine what is the reasonable object size to call it as an annotation. For example, if a statue spans the entire image, it is not an annotation but an image in itself. So these are the few additional features that comes to mind. The key in the first additional feature is that the user has to know an approximate location. So let's conclude. This paper has used 6 distinct locations to test out the given algorithms. So the first type is where we use structured data sets. Basically, a single person collects a lot of images in different camera angles. So we have 2 such locations, Prague and Great Wall of China. We can see Great Wall of China, the results in the bottom left. And next we go on to the unstructured data sets, where we have an assortment of images from the web, and we have to use this to reconstruct the 3D sign. So let's take Trafalgar Square, for example, that's in bottom right. So there are 1,893 images across the web on this particular scenery, and 278 images were deemed to be good to build a 3D reconstruction, and the results are shown below. So the results seem pretty good for the given algorithm, which shows like optimism for any future work to be done. So let's move on. Before we move ahead, I would like to present this video demonstration that we found. The authors had demonstrated how their app works. So we found this to be interesting. So this is a 5-minute video. So if you want to skip or move ahead, feel free to skip around 5 minutes and see the conclusion part. So we'll start the video now.
Searching for a particular image of a well-photographed object using conventional tools often results in a large number of images that are not ordered in an intuitive way. Finding the exact picture we want can mean browsing through page after page of thumbnails. How can we organize such large photo collections in a more intuitive way? In this project, we present a novel system for registering large sets of photos and exploring them in a 3D browser. Our system discovers the relative positions of the cameras used to take each photograph, situates the photos in 3D space, and provides intuitive controls for exploring the scene and finding interesting photographs. Our system takes a collection of photos of the same scene as input. We first find key points in each of the input images, then match key points between each pair of images. Next, we run an iterative bundle adjustment procedure to estimate the parameters of each camera and the positions of the observed 3D points. Once the photos have been registered, they can be browsed using our photo exploration interface. Our system provides standard controls for moving around a 3D scene. In addition, when the user selects a photograph, the virtual camera is smoothly brought into alignment with that photo. Information about the photograph appears in the information pane on the left. Our system provides several intuitive ways to select new photos. One is to select an object. The user can highlight a region of the current photo, and the system automatically finds a good photo of the selection, and smoothly moves the virtual camera to the new photo. During transitions, we use a simple plane-based morph to provide context as the camera moves. A thumbnail pane along the bottom of the screen shows other photos of the selected object. When the user moves the mouse over a thumbnail, that photo is displayed in the main view, projected onto a planar approximation to the selected object. Here, the user selects a thumbnail to see a different view of the statue. We also provide tools for viewing the scene at different scales. The user can step back from the scene with the Zoom Out tool. This finds photos that display a larger area of the scene. The Show Me Similar Images tool finds images of the scene with scale and orientation similar to that of the current photo. The Zoom In button finds details, showing the user what parts of the scene can be viewed at a higher resolution. Here the user selects a photo of the bas-relief in the upper left, and the browser zooms into the more detailed photo. Our second example uses a set of photos taken by one person over the course of 2 days. We registered the photographs and reconstructed line segments as well as points. We can align the reconstructed model with the satellite image to situate it in a geo-referenced coordinate system. We render the scene using the reconstructed line segments. We also project blurred, partially transparent versions of the photos onto the scene to convey more information with a non-photorealistic look. An overhead map is displayed in the upper right. The user can select a photo using the map. Here the user selects a building to see a photograph of it. For this dataset, we can also move left and right along a row of building facades. We provide geometric controls for this type of interaction. For each photograph, we pre-compute a left and right neighbor based on the projected motion of the points observed by the images. We also pre-compute a step-back image, so the user can quickly view more of the scene. In this example, we explore photos of the Notre Dame Cathedral in Paris, downloaded from the web. The user can select regions in the point cloud to find images of an object. Our system also allows users to annotate photos. These annotations are automatically transferred to new images. Here the user labels several regions of the current photo. As each region is labeled, we transfer the annotation to the other photos. The transferred annotations are highlighted in the thumbnail pane. So as not to cover the photos, we'll hide the panes and use a hotkey to step to the next photo in the sequence. As we move to each photograph, the annotations appear. Our system uses simple heuristics to determine if an annotated region is occluded, as in this example where one region is hidden. We can also transfer annotations from other sources, such as annotated images on Flickr. In this scene, we've also added several other annotations by hand. Our annotation transfer algorithm is sensitive to scale. If we look at photographs taken at different scales, we see different annotations. Next, we explore a set of photos of Half Dome in Yosemite National Park, gathered from the web. If the user finds a viewpoint they like, our system makes it easy to find images taken from a similar viewpoint. By selecting the Lock the Camera option, we can generate a slideshow where an object remains fixed in the view. Now we unlock the camera. We can also register historical imagery, such as this photograph of Half Dome taken by Ansel Adams in 1960. Here's our estimate of where Ansel was standing when he took this photograph. Here we compare the photograph to a synthetic rendering from the same location. The white border has been manually added for clarity. Our final example is a scene created from about 80 photos of a walk along the Great Wall of China. We organized about 20 of the photos, seen here, into a slideshow. We have experimented with an alternative morphing technique that creates a mesh from the 3D point cloud, which is used as an imposter for the true scene geometry. This method often works well for nearby viewpoints, but creates artifacts in cases where the matching fails. We hope you have enjoyed our 3D photo tours.
We'll move on to limitations and future work. So the first limitation, of course, is the slowness of the SFM method. Now this can be improved by better order of the feeding cameras and by certain partitioning methods that are mentioned in the research paper. And other way to improve this is to use faster processors. Intel Pentium was the processor that was used for this particular work, and that is not really a modern processor. The modern processors are much faster than that. So we can use alternate processors. Second limitation is lack of georeference data. Now, in a few steps, we have to manually sort of put the 3D reconstructed model onto an overhead map. Now, without georeference data, it makes our job harder. So in the future, as we have more georeference data, we can also automate this process as well. Third limitation is more of an aesthetic one. We can use better UI and rendering. Of course, this is a limitless sort of work. We can keep doing this forever. But yeah, certain things like smoothing the transitions can be done much better. Last limitation, though not exactly a limitation, I would say, more of a future work, is that certain types of images are not registered in this current work. For example, images with low intensity, low illumination, certain angles might not contribute to 3D reconstruction. So there could be better work to even extract the data from these type of images. So let's move on to the next section where we discuss the key learnings and takeaways that we as students have from this particular work. So firstly, we learned the wide variety of applications of SIFT and RANSAC for various modeling and rendering purposes. We learned how we can reconstruct a 3D scenery with a handful of images at different orientations and different types of images. Last but not the least, we saw how computer vision can automate certain mundane manual tasks like annotating images in a very efficient manner. So overall, there have been a lot of breakthroughs in this paper. So with that, I would just like to conclude by telling that that concludes our virtual tour of this particular research paper. So thank you for watching the presentation and have a good day ahead.